He didn't show up, so we'll go ahead and get started. Tonight we have Matthew Eshleman. He's going to talk to us tonight about TDD
for embedded software
and for
courage.
All right.
Let's see if we can get all this working. So just out of curiosity, while we're waiting for this to spin up, how many people have worked on any kind of test-driven development project, whether web-based or embedded? We've got maybe 4 or 5 hands out, so probably 30% of the group. So good. So this will be focused on TDD as it applies to our microcontroller world. My focus will be primarily on professional, product development, but this certainly applies to any of our maker projects as well if you want to put forth that extra effort. Just so you know who I am, my name is Matthew Eshleman. Hello. I've been at this for about 20 years and delivered a whole lot of projects. And I've had about 7 projects now in some form of TDD, either C#.NET or C#WPF, and about 3 or 4 embedded projects now with C or C++. So I've got a lot of good real-world experience, so please don't hesitate to interrupt at any time, ask any questions. Let's make this interactive. So for me, the first time I heard about test-driven development was a long time ago. I was at some random conference that I unfortunately don't remember, and I don't remember the speaker either. But for some reason, this sentence just stuck in my head because of the work environment at the time. But he said, test-driven development gives you courage. And if you've dealt with a schedule-driven product development cycle, when you're getting towards the end and there's millions of dollars of parts getting ordered and factories are getting spun up, the last thing you want is that last firmware change you make to break everything. So we always, at the time I was working for Toshiba, it was always a little stressful right there at the end because truly millions of dollars were on the line. So we were always a little fearful right there at the end. So that comment went straight to my core. But we tried a little bit at Toshiba, but we had too much code from too many places, so we never really got anywhere with that. But finally, about 5 years ago, I read James Grinning's book, Test-Driven Development for Embedded C, and was re-inspired and have driven a few firmware projects now. Okay, so if you don't know what is TDD? It's really simple. It's a process where you write your test first. So you write code that represents a test of the code you're about to write. It's just that simple. If you write that test first, there's a lot of different benefits, and we'll talk about that. But that's fundamentally what that means. When you hear the word TDD, it means you should write the test code before you write the actual target code. So the benefits. For me, these are the benefits I've come through the years. One, it makes us think about our requirements, I think, a little bit more. We have to gather those requirements, talk to people, and that's a really important step that a lot of people try to bypass. And this, I think, creates that speed bump to make sure you gather those requirements a little bit more. And this includes not only a production real product, but your own, whatever you're trying to do with your own maker project. What am I trying to do? What am I trying to do right now? So that test helps you think about that further. I also love the fact that I can test the functionality of my code without the actual hardware if I have to, if I'm doing host-based TDD. And a lot of times these days we're dealing with IoT, the latest buzzword. So our devices are talking to servers. They're talking to some web API, or they're talking to some other devices through Bluetooth or whatever. You can now fake that connection in your tests, and you can test everything in milliseconds, hopefully. And including, in particular, you can test error cases that are really hard sometimes to make happen in the real world. And I give an example there. DNS failure. If you're having to, find your AWS link to send some MQTT packet, what happens if the DNS lookup fails? What does your code do? Well, there's ways you can obviously do that, but it takes a little more effort to do that in the real world, and it may happen accidentally if you didn't plan for it. If you take a TDD approach, you're going to think, I'm doing a DNS query. What happens if that fails? And now you can write a test to decide, what am I really going to do if that query fails? So a lot of times, in our maker projects or even in our professional projects, a lot of times no one has sat down and really written a spec. There's hallway, water cooler specs and notes on boards and random emails and Slack channels and all these ways of finding out what we're supposed to actually do, what that firmware is actually supposed to do. By the time you figure all that out and you write tests for those things, you now have almost a spec. You can just go through and copy and paste the titles of all your tests, and those can almost become sections in a spec document if you needed to. So let's see, code, and for me, it gives me courage. Courage to refactor, courage to rework, and to reiterate, or to rapidly iterate. So what does a test-driven development workflow actually feel like or look like? Well, at the end of this presentation, we're all going to feel that a little bit, at least if you brought your laptops. But you write a test. Well, perhaps that test isn't even calling a function that exists yet, but you've now, in writing this test, you've created the initial idea of how that function is supposed to work. It won't even compile. So now you add your headers. Now you add your empty function. You get to where the test now compiles. You run the test. The test should fail. It better fail. If the test doesn't fail, there's something wrong with the test, most likely, because you've just got an empty function or an empty piece of functionality. Now you develop your real code, the code that's going to go on your product, on your target device. And you just keep developing that until your test passes. And now you've got a passing test. You can now look at the code you just wrote. It might be the ugliest code you've ever written. So now you get to take a break, look at that, and go, now how can I make this better, more maintainable, cleaner, something that other people will look at and not take my name in vain, whatever the case may be. Now you can refactor, and you'll have that test there and whatever other test you've written to protect you and give you that courage to go forth and make that code even better. And you just do this one behavior at a time, just one at a time. So a good TDD environment needs a good test-driven development framework. Tonight we're going to be focused, all the examples, and then our little exercise at the end will be based on CPP test, which is featured by Grinning in his book. There are lots of other frameworks. I've used the Google test there about a year ago on a project, and it was fine. It was perfectly fine. But I am used to CPP test, so that's currently my preference. But I don't have a wide exposure there, so. So now you're probably thinking, well, so I'm building my firmware. Well, where am I building these tests? So you're going to have a separate makefile or separate project or separate CMake, whatever approach you prefer, to build your tests, because you're going to have to fake the hardware. You're going to have to mock certain things that you obviously can't test if you're running your tests on a PC host environment. One big note here is chances are these days your microcontroller is probably a 32-bit microcontroller, but your host PC is probably a 64-bit PC, so when you compile, now your pointer sizes and all these things will be different. So just right from the beginning, set up your project and your makefiles. I'd recommend with just a 32-bit build setup. So depending on what operating system you are using and what for your host tests, you'll have to figure out how to do that. But I will have a GitHub repo with an example that runs in Ubuntu when I'll post that tomorrow. So you will also, because C and C++ all comes together through the linker, you obviously can't have, if you're developing with a bunch of C APIs, you can't have the same C API as a mock and then the real C API all in the same executable. So you're going to end up with multiple projects testing different layers or different slices of your software, depending on the architecture of your firmware. Really important TDD principle, keep it fast. So don't, if you've got some tests, you really want to try to keep everything fast. So that means you don't necessarily have to check all 4 billion possibilities on an integer or whatever. Test the corner cases, test the primary case, and that's probably going to be good enough. And then if you find a bug later, you can add more tests as needed. It's sort of the way I do it. I also use the phrase behavioral driven. So there's a unit test approach where, yeah, you test all kinds of inputs, you go crazy on it. That's great, there's nothing wrong with that. For me, for a bang for the buck for my time, I choose the more behavioral driven approach, which means I'm looking at it from more of a product use case point of view, and I'm testing the actual behaviors rather than every possible input. Like, I don't know, if I've got a date-time conversion thing, I don't necessarily test every single bit of that. But you can. I'm not saying you can't, but for my time and biggest bang for the buck, I focus on use cases and hitting the primary use cases. Okay, so since the last time I gave this presentation about 3 years ago here, one of our projects ended up being on-target test-driven development. So all the tests actually executed on the microcontroller. And this was the first time I'd been exposed to that. And it was pretty cool. I mean, it's great because now if you have assembly optimized code, you don't have to worry about that on your PC side, for instance. So that's wonderful. That's really the main advantage. You're really exercising all of your drivers, you're exercising the actual compiler that is your target compiler, et cetera, et cetera. So that's a great advantage. The unfortunate disadvantage is it's just slow. Whereas I converted actually a set of tests for this customer from on-target tests to CPPU test-based tests. Exact same tests, just different environments. It went from basically a 30-ish second round trip time to 30 milliseconds. And that's what you want. At least that's what I want, because I start to fall asleep in that 30 seconds. So that was really tough. So what we've ended up doing as we've transitioned to a new product for this customer is we now have a mix. For all of our application layer code, for all of our middleware-ish code, we are hitting it with CPPU test, and then we have on-target test for our drivers. And that all sounds great, but even the drivers is kind of rough because drivers talk to real hardware, so you can't generically test that. So it's not necessarily a panacea, but it's a great way of even testing. It's a nice balance, a nice bang for the buck. And if you want more details on that, Quantum Leaps at statemachine.com. There's a link at the bottom here. They're dual source, so you've got GPL and a commercial license, but they've got a whole set of tools that you can look at to see a way of going about this. And if you go look at that, what you'll see is they have a very relatively thin shim of code that runs on the target, and it expects to have a communication channel to your host PC. And then the host PC is running a scripting language, and the script is sending commands to your custom test environment on the target and receiving data back. So your actual test logic is still running on the PC, which is great, so you can flexibly change that script. One of the disadvantages there in my mind, though, is if I've got a constant, for instance, and I change it in the C code, now I have to go find it in the tickle code in this case. So there can be some friction there that I didn't quite like. All right, so a real quick example, high-level project and build setup. So let's say we have, this is kind of a fairly standard firmware architecture. You've got some kind of app layer, and maybe you've got these different middleware things. Some people call them controllers, some people call them services, some people call them managers, whatever you want to call them. But each of these services might be dealing with a particular communication channel or a particular piece of hardware and doing the housekeeping work for that, and leaving the app a kind of more abstract API for interacting. And then, of course, there's always a hardware layer. There's your HAL, or your driver level, whatever you want to call it. So a example build or project setup, you might have a separate project just for your app layer. So that would be a test project that only tests your app. The app in that test environment is interacting with mocks, with fake services. And we'll talk about that more here in a second. And then you might end up with a service layer test project that tests all your different services or your managers or your controllers, whatever you want to call them. And those are interacting with a fake driver level. And in your CPPU test environment, you can, of course, see what they're doing and make sure they're doing what you expected. And we'll see some of that here in a minute. Oh, and then, of course, let us not forget the real firmware project. This is actually what you're going to burn onto the chip and ship to your customers or play with on your maker project. OK, so I've said the word mock a few times. Oh, is it break time?
Yeah,
Pizza finally arrived. Yay.
There are no cups yet. It's coming back. So you know,
We've had pizza delivery problems tonight. All right, so we'll take a 5-minute break, or do we want to wait for cups, or?
Take a 5-minute break.
Okay.
Don't hold your breath on those cups ever coming back.
All right, 5-minute break. Anybody have any questions yet before we get started again? Oh.
You don't want to ask a question when it's not recorded, right?
Oh. Did you stop recording?
That's when you ask the no.
For the break? Wow. Okay.
We're still streaming the video, but I'm here to record it too.
Okay.
Up there to say.
Okay. Tell me when you're going to start recording, or
Whatever you want. When you tell me.
yeah, go.
I do have a question. What about runtime? Hold on. I got a question on the head. I, as the mic, go first.
Oh. Well, I'll repeat the question. It's okay. What was the question?
Runtime tests.
Runtime test.
Even tests running in a pre-build, pre-release environment. Something that's more that's running at startup, for example, to test your hardware and report back.
Oh, like a power on self-test?
Yeah.
So that's a different topic. But you can TDD your power on self-tests, because I just did that for a customer recently. So yes, if you have a sequence of tests, those are going to be interacting with some sort of API. You'll mock that API. You'll see more. You'll probably get a better vision of that here in a minute. Is there another question over there, I thought? No? Okay. All right, we ready to get started again? All right, here we go. So we mentioned mocks. Everybody's got pizza going into their bellies now, so that's great. Hopefully not fake pizza. So a mock is this fake thing that your real code is going to talk to. It's going to have the same API or the same interface as the real code, but your test environment on your host PC typically will be able to interact with that, observe what happens, and use that to make your tests intelligent. So we have an example right here. So we have a theoretical API, or sample API, ADC underscore get sample, and it returns a unsigned byte. So this is CPPU test style. You see a mock actual call, and you have to use a string there, which is fine. And then you can return a value. And you'll see how this is used in a minute to set up the mock to return whatever value you're wanting to test. And so this is very useful. So you can test a very high ADC value, you can test a very low ADC value, you can test whatever you want, but your test will drive that instead of you having to deal with the real world. And now here we see an actual test using this approach. So here we have a test for a module called the temperature monitor. And we've declared this test. The first read returns OK, even when too hot. So even if the temperature of this that we're reading off through this ADC is too hot, we'll still say we're OK for that first read. So that's our spec that we had. So you can see there on that first line, we're calling expect one call. So we're telling the mock subsystem that we're going to get we're going to get exactly one call to ADC get sample, and we want it to return a value. And I've got a type def, and this, by the way, is important if you want to do the exercise at the end. So there's a value that's too hot, and I'm telling the mock to return that. So now I call the actual code under test, which is our temperature monitor is OK API. And then we check our results. So we expect it to return true. So that's that check equal true comma OK there. And then we also call this mock check expectations. And that mock check expectations confirms that the code under test actually made that call to ADC get sample. So we've confirmed two things. We've confirmed that it returned OK, as we expected, and we also confirmed that it actually called this hardware code that we expected under this condition. So that is a simple single test right there. All right, we've got a bunch of lessons learned to talk about real quick. So one of the first lessons for me is don't be so strict. In a production commercial environment, you tend to have these public APIs and then private implementations. You keep doing that. But don't be afraid to open up a little hole, a little back door to let your TDD environment have an easier job. You don't have to be so strict about that. Just mark it clearly. This is for TDD only or whatever. At least in my experience, that helps a lot in weird cases where you're like, how am I going to test this? And you'll see some examples of that in a minute. Threads. Don't test threads. It's fundamentally I guess you can do it, but it's going to violate several issues. One, your threading environment on your host PC is going to be radically different from whatever operating system or real-time OS that you're using on your microcontroller. So behaviorally, that's not a fair, legitimate test. The other issue, of course, is threads block. They love to sit on semaphores or mutexes, or they love to sit in a delay loop or whatever, and that goes against one of our goals, which is to make these tests as fast as possible. Because, oh, I forgot to mention, part of why you want them fast is to encourage their use. If it takes 20 minutes to run a bunch of tests for some strange reason, nobody's going to want to run that. You want it to be so easy and so fast that everyone on your team will be running those tests all the time. So I mentioned threads. Typically, your thread is going to have some sort of initialization or startup or spinning up the thread. Don't bother to test that. You want to test the meat of the thread, what it actually is doing, if possible. And if you follow my advice in one of my other presentations, which is my preference for event-driven software, this becomes even easier to do. And I didn't include it because I knew we might run a little short on time tonight, but there's a slide at the end we can get to if we do have time. Speaking of time, so typically we have a lot of elements of time in our software, either calendar time, which I try to avoid that as much as possible, but in particular, delays, loops, do this in 50 milliseconds, do this in 200 milliseconds, do this in 1 second, do this every second, do this every 10 seconds, do this every 50 milliseconds. You'll run across this a lot in our embedded software. So how do you deal with that in a test? How do I test, did my code do this every 1 second? Well, let's see. So as an example, let's take FreeRTOS. FreeRTOS has a timer API. Lets you create timers, start them, stop them, etc. So what you end up doing, of course, is you mock and create fakes, I think is the better term in this case. You fake the FreeRTOS timer subsystem if you're running on FreeRTOS. So now, whenever you're running on your host CPPU test-based environment and you call FreeRTOS create timer, you're actually just kind of keeping a record of that in your mock. This is a little more sophisticated than just that mock. You're actually having to put real logic in there. I think they call that a fake versus a mock. So what you end up with might be something like this, what you see here on the screen. You might end up with this cool function, move time forward. And move time forward will go through all the timers that you've kept track of in your mock and find them and fire them off just like FreeRTOS would. Except now it's happening instantly on a PC instead of truly having to take 1 second. It's a fake time frame. And the key is your test environment controls that time. So here's a diagram example. So you got your test code, your test framework, and you have your firmware under test, which might be calling the FreeRTOS timers. And then you've got, so your test code is going around and moving time forward. The beauty of that is now it's instant instead of taking actual real clock time. So here's an example. We have some app, and it's supposed to do a retry if it doesn't receive some sort of acknowledgement after 10 seconds. And this app, we're expecting it to call a cell service and send a startup packet. And if it doesn't get a response, then we expect it to do it again. And that's what this test you can see here. So we moved time forward 10 seconds. FreeRTOS uses callbacks. In this example, those callbacks that happen in there are going to put messages in an app queue. And then we can check to see if this actually happened. Did it during this 10-second period, did it call the cell service send startup packet again? And we can check all that. And this test will run in microseconds instead of taking actually 10 seconds. Any questions? And hopefully this takes us eventually to this place in time. Green lights, lots of passing tests, which gives us wonderful courage. So tell you what, we moved pretty fast actually. I took out more slides than I realized. So here was an example of the don't test the thread, test what's inside the thread. So you might have this app task, and it might run with some sort of state machine. And we process this queue. So we break this out so that the TDD environment is processing just this one thing. And then that way, we're not in this infinite loop, which the threads are always in an infinite loop. So we're breaking through that infinite loop and letting the test environment control that one thing of what the thread is really doing. So that's the kind of thing where you have to do the back doors, basically, into your module. This would normally have been private code that you would have kept hidden inside your module. In this case, you're given a little entry into the internals of your, in this case, an app process or an app task. Let's see. So here was one more time example. So maybe your app has a requirement to perform some sort of reset if you press and hold a button for 8 seconds. So here, this is the ARM HAL layer for doing a microcontroller reset. So we've mocked that HAL API right there. And we've got some sort of button manager code, which we're not going to talk about. But when it hits in this case, we've actually removed time. What we've done is we said we've got this middleware service, and it can generate these events. So we just generate the event instead of actually implementing that code in the test environment. So the app gets this event, and we make sure that when the app gets this 8-second press and hold event, that it calls the microcontroller's reset function. So that's one more example. All right. So who brought their laptops?